Testing, testing. 1, 2, 3. Test, test. Hello. That's better. Good, good, good. Just need to get the picture. Can you tell it's been a little while since I've done a live stream? A professional person would have made sure all of the camera and all of that was plugged in before we started streaming, but you know. There we go. Oh, jeez. There we go. There we go. Hello. Welcome. Let's see here. So, good. So I expect what's happening right about now is that a bunch of people who are who didn't get the announcement have shown up to the room and are wondering where I am. Probably that was happening a few minutes ago. Hopefully they realize that there was an announcement made. We'll see. At any rate, shout-outs in the chat. Hello, chat. How is chat doing today? Are you guys, how are you guys doing? Can I get a whoop whoop in the chat? Good, just tired. Ready to start the week. Yes! Yep. Yeah, I hear that. It's been a bit of a rough weekend in our place. Good. So, well, hopefully, hopefully I last through the whole 3 hours. We'll see. I'm definitely on the other side of it and just sort of, you know, I'm in the phase of it where I'm trying to, clear out all the accumulated biological detritus that's gunking up my system, you know? I believe I'm over the active part of the infection, and I am in the phase of cleaning out the gunk. But, you know, if I cough and spew a little bit on camera, I apologize. It's not my intention to do so. It's just one of those little facts of life. Good. Well, we might as well get on with the show, as it were. Let me just see what our viewership's like. 9 people concurrently watching? I mean, I've seen worse. So, good. Kind of wondering what the latency is like. Okay. I want to check the latency on the chat. So, in a few seconds, I'm going to clap my hands. If you guys could prepare like the word clap inside of your text, your chat box, and then press enter when you hear the clap, that'll give me a good idea of what the latency is. So if you wouldn't mind, I'm about to do it. There we go. 1, 2, 3, 4, 5, 6. About 10% latency is not too bad. Pretty good. Excellent. Good. Okay. I can work with that. So, couple of announcements before we get into it today. Number one, obviously, the lecture this week will be online via live stream because I don't want to spread the coof around, so all of that stuff. Also, next week we're having a test. We're having our midterm test on May 24th at 2 p.m. I'm currently negotiating with the powers that be to get us a room for the occasion. So, I don't know what room they'll give me. There might be a small adjustment on the date or time. I don't think there will be, though, because it's the summer. So, yeah. May 24th at 2 p.m. That'll be the midterm. Please bring your computer. And please make sure it's charged. You will need it to write the midterm. So there you go. So that kind of means that we have this class, then tomorrow's class, and then the midterm is on the same day that we have classes on the 24th. 24th is going to be a big day of 1MD3 for you guys, I guess. Given that we also have class that day. I wanted to book it for the 24th since, if you have a job, it's more likely that you'd take Monday, Tuesday off because you have this class. Although I suppose there could be people some working in the afternoon, but it seemed more kind than occupying your Friday with it, But anyway. So, especially, what with the gas prices, topical topic, ho-ho, with gas prices the way they are, I'm sure everyone wants to minimize the amount that they have to commute to get to the university, eh? Anyway, so let's talk about our lecture material for today. So, last time we were talking about data structures at some length. We talked about lists, sets, and dictionaries. And we were just about to get into a section on problem solving. So, the problem that we're about to go through is a reasonably famous problem, or it's a member of a famous class of problems, shall we say, in computer science. So, it's a problem that while it has several simple algorithms that can solve this problem, these algorithms are, deceptive in that they don't always work for all instances. And, it's an interesting problem to sort of tease out the corner cases in. So, we're going to be talking about the make-change problem. So let's imagine a scenario. Let's say that you are a cashier and you have to compute the amount of change that is due from a certain transaction. So you have the amount of change that you have to make, and you have a set of coin and bill denominations before you, and you must give out change in such a manner as to minimize the number of coins and bills that you give out. So, excuse me for a moment. So, consider the following. We have, if we use the standard set of Canadian coins, and we have a amount of change that we have to give back equal to 185 cents, then we would obviously be giving 1 loonie, 3/4, and a dime as the coin denominations. But the question is, how do we encode this as an algorithm, right? So, before we encode it as an algorithm, we have to decide what our inputs and our outputs are going to be. So, for inputs, we want to take in the coins themselves, like the denominations of the coins. So we're going to take in a tuple of coin denominations as integers, and we're going to take in a target value, also expressed as an integer. Our outputs in this case are going to be a dictionary where keys are coin denominations and values are integers corresponding to the number of coins of each denomination that form the target value. So, let's whip up a quick implementation of this. Def, make change. We have our coins, we have our target value. Here. So what approach would we use to calculate this? Well, one approach that we might use is we start with the largest coin denomination, see if there are any coins, see if we can fit any of that coin into the target value, and then, take that many coins, set it aside, reduce the target value by that amount, and then continue on, right? So, let's say while target is greater than the last coin value, say coins -1, that bakes in a couple of assumptions. But let me just get this part out first. We'll say that, first of all, the output is an empty dictionary. You know what? I'm going about this all wrong. Let's go by indexes over the coins instead. That makes more sense. So coins at I, while I is less than the length of coins. We need to remember to increment I output at coins at I is equal to the target integer divided by the coin denomination, right? And then we update target to be itself mod that same value. So remember, this is, of course, whole number division. So the, the number of times you can fit this number inside of this number is going to be the result of this operation, and the number that's left over is, of course, modulus. And then at the end, we can return the output. So let's run this guy, see if it comes up with the expected result. So Canadian coins. There we go. $1.85. Print. Make change. Canadian coins. Change. There we go. Let's compile this guy. Make changes not defined. Ah! Now it is. There we go. So, if we take a look, we get 1 loonie, 3/4, and 1 dime, just as we had anticipated. So this is good. This works, right? The procedure that we're using, that is, taking out as many of the biggest coin as we can, and then moving on to the next largest. This is known as a particular type of algorithm called a greedy algorithm. The reason it's called greedy is because it takes, at each step, it's taking as much as it can with the current number under consideration. However, so this is the implementation that you find in the slides. Now notice that they're counting up instead of down here. If you wanted to make this protect this algorithm against an assumption about what order the coins are in, it would be reasonably easy to, put a sorting operation in there. So yeah, you'll notice that this is very similar to our solution, except this solution decides not to use a modulus and it's counting down rather than up. So yeah. So here's an interesting thing to consider. Does this solution work for every, okay. So we have a slightly more advanced concept of what it means for this algorithm to work in this case, right? Because, like, your sort of your basic acceptability criteria for this algorithm is that change is returned. Whatever combination of coins you've produced, numerically they add up to the target value, right? That's condition number one. You have to implement the making change part correctly, right? But there's another sort of hidden, well, it's not hidden. There's another requirement on this, which is somewhat more subtle. We want the algorithm also to give the smallest number of coins possible, you know. And it turns out that that's actually useful. Like, I was at a 7-Eleven buying Gatorade for certain reasons over the weekend, you know. And, like, I give the guy a $20 bill, and it's like, you know, $4. The transaction's like $4, and this guy gives me back, like, my change entirely in, like, loonies and toonies, and I'm like, man, you don't have any bills? Come on, man. But yeah. So it's like, the fewer coins you give out as a cash register, the fewer times you have to be resupplied with change by the manager or what have you, so that actually has an impact on the efficiency of your operation to give people change in larger bills, which, you know, people generally prefer it anyway. So we have this requirement that we want the minimum number of coins possible. Well, consider the following, and this is kind of a constructed example, as I'm sure you would never find a country with currency in such denominations. But let's imagine we had the following scenario, right? What if we had a target number of 14 and a coin set 1, 5, 7, 10? Now, just looking at this as a human being, obviously the solution that produces the fewest number of coins will be you have 2 7-cent pieces. However, if we apply the algorithm that we designed here, then what we end up with is 1 10-cent piece and 4 1-cent pieces. So we end up with 5 coins instead of 2. Well, it turns out that the greedy algorithm only gives optimal results assuming that each coin is at least twice the value of the previous coin. Unless this additional condition is met, you may not be getting optimal coin values out of it. So this is an example of a type of problem that we have in computer science called a non-polynomial problem. So you can imagine the algorithm that we wrote here to compute change was reasonably simple. But it doesn't guarantee that you get the optimal number of coins. In order to guarantee that you get the optimal number of coins, you would have to introduce backtracking. Pardon me. So, rather than the way this algorithm works, where every time you make a decision, that decision is set in stone and you assume that's absolutely correct and you move on to the next case, with a backtracking algorithm, each decision that you make is provisional, right? It's like, well, I have to make a decision to be able to expose the next set of decisions, but I'm going to sort of keep track of it so that I can return to it later if it turns out that this decision wasn't a good one, right? These types of algorithms exist all the time. You can kind of think of it as like searching a space of possible solutions. Such problems are generally called NP-hard problems. So the reason it's called NP-hard is the NP stands for non-polynomial. So a polynomial, what that means is it's a characterization of the algorithm according to the function that we would use to describe how quickly the runtime grows as a function of the input size. So in this case, the more different coin denominations you have, the more decisions you have to make, the more of a search space there is, right? So basically, each additional coin that you add multiplies the amount of space that you have to search. So this is not a polynomial. This would not be polynomial. This would be an exponential relation. Non-polynomial problems, they're kind of, it's a bit of a double-edged sword. We generally refer to them as algorithms which there's no proof that an efficient algorithm exists for it. And, you know, it's interesting because non-polynomial problems are also what make encryption work, for example. So the only reason encryption works to protect data is decoding encrypted information when you have the correct information, i.e. the encryption key. That is a very fast algorithm, right? It's like, linear, or, it's a fast algorithm. We'll get into this a little bit more when we talk about big O notation. A non-polynomial, so if you don't have the encryption key, it becomes very, 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 very time-consuming to decrypt that information. Now, it's always possible to decrypt the information without the encryption key, right? The only question is, how long is it going to take you, right? Because it could take you longer than the age of the Earth so far, or some similarly ridiculous number. And if the encryption keys are being updated every couple of hours, then it's effectively impossible for you to break the encryption. Passwords kind of work the same way, right? Like, you guys, you know how, there's been a push to have longer and longer passwords over time? The more characters you put, each additional character that you put in a password multiplies the number of possible passwords that can be represented. So having, if you have assuming you just have, assuming you just have numbers as your password, each additional number that you put in a password multiplies the number of possible passwords by a factor of 10, right? So, you know, a 4-digit password, you know, there are only 1,000 possible ones, you know, but a 7-digit password, there are 1,000,000, and it takes a lot longer to process 1,000,000 things than 1,000 things. And the more characters you can throw into that, like each additional character that you throw into the password, increases that that factor, right? You know, if your password system accepts 35 possible characters, then the number of possible passwords is 35 to the power of the number of characters in the password. So anyway, solving these types of problems, like solving an NP hard problem in polynomial time, or proving that NP hard problems could be solved in polynomial time, it's kind of like the speed of light problem as applied to computer science. Like, there are lots and lots of people who don't know enough about physics, or know something about, but not a huge amount about physics, who are like, you know, oh, wouldn't it be awesome if we could, you know, travel faster than the speed of light? And then you have, like, anybody who's, like, an actual physicist who's like, well, you know, I don't think that can happen, really, you know? Excuse me. At least not under normal circumstances. And the NP hard problem is kind of like that. It's like people who are, like, know a little bit about computer science think that, you know, oh, wouldn't it be so cool to be the person who solves the P equals NP problem. Polynomial equals non-polynomial. But then you would break, like, all existing encryption. And that, you know, that basically means that, like, the algorithm that would solve P equals NP is like would have military applications, you know? So, I don't know, maybe they've already developed it, but they just don't let us have it because, you know, it's like the cure for cancer. They have the cure for cancer. It's just, you know, they won't let you have it because it's like, I don't know, some conspiracy reasons. Anyway. So anyway, that's topic 4. Any questions before we move on to topic 5? This is your time to ask questions. I'm sorry I'm not very high energy today. It's, you know, I'm doing my best. Can I get a thumbs up from the crowd? Just to make sure that you're all still here and alive. I haven't lost you, have I? Cool. Awesome. By the way, I like some of the screen names going on here. like Daily Tomato. That's cool. I like that as a name. That's like indie video game company material right there. Like indie game studio name. Yeah. All right. So, let's talk functions and recursion. So, we've used functions a lot, but there's a lot more going on with functions than you may at first be aware of. So we're going to poke around and check out some of the bits and bobs, some of the nuances of functions, and we're going to introduce a concept called recursion, which is a very, very important concept in computer science. Ordinarily, it's considered a very difficult topic for people at an introductory level. So we're going to take it slow, and hopefully y'all get a good idea what recursion is by the end of this. So, functions. I won't patronize you too much, because, you should all know what functions are after having already submitted assignment 1 yesterday. So a function, of course, is a way of grouping together a sequence of operations under a common name so that we can refer to it multiple times later. Another way of thinking about functions is that they provide algorithmic abstraction. They allow you to take a bunch of operations, a bunch of statements, package them up, give them a name, so that you don't have to think about the contents of it. As long as the output behaves as you expect it to, given the inputs, you don't actually have to know what the function contains. That's the whole advantage. You can construct a black box around the function and just exclude it from your mind. So, of course, we're all familiar with the syntax of functions by now. Here's an important piece of nomenclature, though. The parameters that are provided in the function definition itself are known as the formal parameters. The formal parameters are the variable names that are used inside of the function itself. The values which are provided, whether they have been sort of assigned to variables or not, these are the actual parameters. They are actual because they are in actuality. They have actual concrete values, whereas formal parameters will have concrete values at some point, but not yet. When a function is defined, the formal parameters are included in the definition. When a function is invoked or called, the actual parameters are provided. So, during invocation, there's an implicit step. So, because Python uses pass-by assignment, this guy here gets assigned to this guy as a variable name as an implicit step as soon as the function itself is called. Right? So you can think of it like immediately after change, there are 2 lines of code which are implicit. They're not, they're hidden, right? And that is target equals T and coins equals C. Right? So I mentioned this before, but the thing that needs to awaken in your brain is a realization that, oh, well, if that's assignment, then everything that's true about assignment is true about that step. And it's like, yes, including aliasing. So this guy right here is a list, which means that C, its actual value, is a memory address where this guy is stored, right? So coins is going to end up as an alias of this data structure. Pardon me. Which means any modifications that were made to coins inside of this function would be made to C as well, essentially violating scoping rules. And this doesn't happen with tuples, so that's just useful to keep in mind. So here's another interesting thing. You can also assign default parameters. So if you're writing a function and you think to yourself, well, this function should have this value most of the time, and, you know, unless specified otherwise, it should be this. You can set a parameter as having a default value by including a small assignment statement inside of it. So, if, for example, I say coins is normally equal to 200, 100, 25, 10, 5, right? So A, you put these at the end. Like that. And B, that means that you no longer have to include that. Come on, keyboard. There we go. This will work exactly the same as it did before. However, we retain the ability to include other coin denomination sets. We just have to say them explicitly. So, for example, print make change 14 from coin set 1, 5, 7, 10. And you can see that that didn't even... Oh, right, because I got them in reverse order. There we go. So you can see that essentially what happens here is that if a parameter is provided, that will be the actual parameter used. But if no parameter is provided, it will default to the specified default value, which is a very useful thing. So, you can also specify, if you have a function which has multiple multiple default values or default parameters, you can specify which one in particular you want to assign to by including the small assignment statement when you call the function instead. So a good example of this is the print function. So you'll notice that print has a number of optional parameters here. Separator and flush file. So, if I were to say, print, this is a statement, and then I wanted to say, I wanted the end character to be 2 lines instead of 1, right? I say end. I specify which one, and then it adds that. If I want to say separator, or if I want to specify what the separator will be, maybe make it a tab, and then I say print 1, 2, 3, 4, 5, you'll see that it inserts the tab character between the things I've specified for it to print, right? You can even say, like, a new line, you can say weird characters. There you go. Whatever you want, right? But you can do that on either side because you have basically... So normally how it works with functions is which the actual parameters are lined up with the formal parameters by their position, right? Positionally with respect to the arguments. If you're specifying the formal parameter name, then you can do them basically in any order you want, because it doesn't matter anymore. Right? Hopefully that makes sense. And of course, if they're optional, they can be omitted. So we've already talked about scoping, but let's talk about it again. Because, So, just give me a second. Good Lord. So, scoping is a very important concept in when you're designing a program. It basically tells you where your variables exist and where they don't exist. I'm going to do the demonstration here in Python Tutor because it just makes much more sense there. So let's say we have a function, right? Even this one will do. Right? And let's pull in this here. Right. So, when we launch and execute a function, one of the things, okay. So this is how your computer executes functions, okay? There is a structure of memory inside of your computer, which is known as the call stack. The system call stack, the function call stack, or reverently, the stack. Some of you may have encountered Stack Overflow. When Stack Overflow is like a very obscure error that's very difficult to diagnose, and it's a problem that you get when you get too many things on the stack, and that's, that's where Stack Overflow gets its name from. So essentially, the way that the stack works, when you open up a program, a stack frame is created. That stack frame contains a certain amount of space for memory, or a certain amount of memory which is used for variables, right? It contains information relating to which part, like what, where it's returning information to as well. It contains a lot of information, and we don't need to get into it, all of it. But it's important to note that local variables are stored inside of the stack frame. So, in fact, what we mean when we say a local variable is we mean a variable which has been stored in the stack frame of the particular thing which is executing. So, when we execute a function, like we are doing on line 11 here, that creates a brand new stack frame, right? It puts it onto the stack. So the computer is always only executing the top frame in the stack. That's part of what, makes the stack work. The top thing on the stack is always the thing that's actively and currently being executed. So if this function were to call another function, that function would have another stack frame put on it. And we'll see this when we do recursion. But when, for example, output is created as a variable, right? Or I is created as a variable, the place that it's being stored is inside of the function's stack frame, right? So it, it does its execution thing. The dictionary gets populated. Then, the return value is decided, right? The return value is returned to the main execution, and then the stack frame disappears. Once the return value has been returned to whatever invoked the function, that stack frame disappears. It's deleted. The resources are freed so that other functions can be run on the same chunk of memory. So, you'll notice that I does not exist anymore, right? The stack frame that contained I no longer exists. So referencing I at this point would result in an error. So for example, if I wanted to print I after this, the last thing this thing is going to do is it's going to say name error, I is not defined, because of course it isn't. If you take a look inside of the current, because the place it's going to look for I is inside of the currently executing stack frame. There is no I in this stack frame. It was in the stack frame for make change, so this constitutes an error. So when you are inside of a stack frame that has another stack frame behind it, variables inside of the global frame here are, not coincidentally known as global variables, right? So change, in this respect, is a global variable. even though change is being assigned to target, you know, way back here, when the stack frame is created, the variable change itself is global with respect to the function. So we can actually get the function to access information from the global frame. But we just require a little bit of, we need we need an extra keyword. So let's say times run is equal to 0. If we say use global variable times run plus equals 1, then you'll see that times run exists inside of the global frame. When we execute this statement on line 3, you'll notice that this function makes a modification inside of the global frame. It only does so because it's been given explicit permission to. Because this is the line where, line 2 is the line where we give it explicit permission to do that. Otherwise, it wouldn't have access to it. If you tried to reference times run without including this line, it would think that you meant a local variable. It would look for it. Since it's a plus equals operation, it can't be defined by that statement, so you would run into another error. Does this make sense to you guys? Give me a thumbs up if this is making sense to you guys. Good. So, I have spoken at length about, why you shouldn't use global variables, or you should avoid their use. Pardon me. So we'll just sort of, please don't use global variables very much. Each time you use a global variable, that becomes an implicit input and output to your function. It makes them far less modular, less easy to debug, and just makes everything more difficult to work with. So try to avoid using global variables. The temptation can be great. I will tell you right now that use of global variables inside of assignments, for instance, you're going to, by using global variables, you'll basically be making assumptions about like how often and when your code is going to be your code blocks are going to be executed, which are most likely wrong. So I recommend not using global variables at all. Pardon me. Good. So, right. Moving right along. So, let's talk about some aspects of software design. And again, these are things we've kind of already talked about, but they bear repeating. So, software design principles. The correct way to think about software that you write, the way that you want to design software, you want to design it like it's Lego, right? you want to design it so that there are a large number of simple components which can be clicked together easily, which can be used to construct large and impressive things, which may or may not be related to the original brick structure, right? So, like if you think about a Lego, right? Lego is like, it's a very simple thing, you know? It's like, it fits on other, like you can connect it to other Lego in particular ways, but the ways in which it can be connected are reasonably limited. The beauty and the strength of Lego is in, you know, you can make a whole bunch of different decisions about how to connect them, and using those decisions, you build up like a house or a dragon or whatever you want to build. Software ideally construed is very similar to this. So the idea is, whatever programming task you have in front of you, you want to break it down into small parts that are 1, reasonably self-contained, 2, achieve a clear purpose, and 3, can be reused. So, like, if you're writing software and you're finding that you're using copy paste to, like, oh, I wrote some code up here, I need it 3 more times, so you just copy paste paste paste. That is a situation in which I would like you to consider using a function instead. Even if you take a function, like even if you take those lines of code and generalize them slightly so that they're applicable in slightly more situations, you know, add a parameter or whatever, that can be a huge improvement. So, what you have to do is you have to develop the skill of taking a problem, breaking it into small components, solving those individual components individually, and then recomposing the solution back from them. This is a I would say this is not just a important skill in the design of software. This is an important life skill as well. You know. When confronted with big problems, it's very useful to be able to, you know, shave problems, related problems off of the larger problem, solve them individually, and then smack them all back together. It's a very effective problem-solving strategy. So, in software, what you get as a result of this is a property called abstraction. So, the more highly abstract your code is, the easier it is to work with, generally speaking. It's like, in order to program, you have to have a reasonable idea of what the things you're programming with are actually doing, right? But by writing a function, you can take all of the steps that are required to perform whatever computation that function is computing. You don't even have to think about them, right? They're off in one corner doing their own thing. All you have to know is what the output's going to be if you give particular inputs. This allows you to, like, work with much, much, much more instructions than you would be able to without this property. Large programs will have a lot of functions. Each function should be relatively small and designed to do one thing. just for fun, I'll show you an example of a large program. Since I'm at my, I don't know, maybe this is of some interest, but let's see here. So, this is my thesis. This is what a large... Now, this is written in Haskell, which is not a language that we are learning in this class, but this is a large program, right? So each one of these with the same name, that's a function in Haskell. Haskell is a functional language, so pretty much everything is a function. But you can see that, like, large programs get very large. This is, if you're wondering what this does, this is basically a compiler. It takes a hardware description language, and it compiles it to a different language that allows me to do some theorem proving on it. But, yeah, so, how many lines? 4,000 lines of code here. I measured it across, like, all of these files. There's something like 12,000 lines of code here. And it's interesting because Haskell kind of has a compression ratio where, like, one line of Haskell is equivalent to 20 to 30 lines of code in any other language. So, programs get big. And when they get big, they get unmanageable. Unless you have built in appropriate abstraction mechanisms. Because, like, I don't care how brilliant you are. No human being on the planet is going to be able to simultaneously hold in their brain, 30,000 lines of code. It's just not physically possible. But if you take into account, or if you consider something like Twitter, right? Twitter is actually reasonably simple, right? All it really is a database. When you tweet something, all you're doing is you're taking some text and you're storing it in a database. When you view tweets, what you're asking for is, like, a certain selection of tweets from the database that are filtered by, like, whether or not you follow the person, and ordered by the order, like, ordered by the time with which the time, the timestamp of the tweet is what they're ordered by, and stuff like that. When you like someone's tweet, all you're doing is updating that database entry and incrementing the number of likes, right? So, like, while Twitter, like, as a monolithic sort of entity, seems like a very complicated thing, it's actually very simple if you break it down in terms of its essential operations. Right? And that's what you want your software to be. You want it to be reasonably simple if broken down into its essential operations. So, another, like, really crucial aspect of working with large programs is documentation. So, when you're writing programs, especially programs of any size, or programs that you would expect to spend, months working on, it's very important that your program be documented, right? What documentation does, like, there are several ways to document. But, the basics is, when you write a function, there are going to be implicit assumptions that you make about the input into that function. Those assumptions should be stated explicitly somewhere, preferably in a manner that's easily retrievable by anybody who's using your function. The way that Python solves this problem is it provides what's called docstrings. So if you have a function, you open up 3 quotes, and then close 3 quotes, anything that you put inside of here will be visible if you call the help function on this function. So, assumes coins is in descending order. That's an important one, right? So this particular algorithm assumes that this, whatever is provided here as coins, that it's going to be in descending order. If a person didn't know that, they would, they might get lucky and just provide a list of coins in descending order, or they could, not do that, provide coins in random order or ascending order, have the algorithm glitch out, and then, assume that it was poorly written, which might be the case, in fact. However, if it had been documented, in order to use this function, you need to provide X, you need to provide this input in this manner, then, that basically that puts the burden on the person using the function rather than the person who wrote the function. Generally speaking, software is only considered, software engineers generally only consider, valid uses of their software, right? It's like, I don't have to deal with debugging your case because you're not following the way that it's been documented, right? You're not following the assumptions that have been built in that I've stated, so I don't have to fix my software. You need to fix the way you're using my software, right? So that's one. You need to tell people how to use the software. Number 2 is what conditions are satisfied after execution. What does it actually compute? And of course, this is, as I said, assuming that the assumptions have been satisfied. So, the fact that our make change function returns a dictionary, that is a post condition, that is something that is produced, that is a guarantee of the function. It should be stated. So, if we were to write some documentation for the make change problem, we would say assumes target is an integer and that coins is a sequence of ints in decreasing order. Returns a dictionary with a key for each entry in coin and a corresponding int for the number of coins in that denomination. So, this type of documentation is particularly important in Python because Python does not constrain types. Even if you specify typing inside of a function, it functions merely as a suggestion. It's not actually binding. Basically, that stuff has to be enforced at the level of you, the user. I almost said you, the loser. You, the user. So, the fact that target is an integer needs to be stated because there's nothing about this that suggests it would be an integer. Now, this is different, like in languages like C, where in C you would need to say int target, and int array coins, right? the typing information is built in. Because Python doesn't require typing information, that's a huge thing that you should include in documentation. Good. Okay. If you guys don't mind, I'm going to call a 5-minute break here while I put my organs back in their correct positions. We'll resume class at 10:50. Okay? I'll see you then. And we're back. Hello, everyone. Good. We return. So, thank you. So now we get into recursion. Recursion is like a very beefy topic. It's got some math going on. So if you don't get it at first, don't feel too bad, because it's, not an easy topic. Hopefully by the end of this, you have a better idea. But recursion is a formulation of a function where the function itself is called within the function. Sorry, give me 1 second. So, sometimes you have a problem where the structure of the function, the structure of the algorithm suggests calling of the same function over a smaller problem of the same type. This is like generally an excellent case where you would want to use recursion. Pardon me. Recursion is also an alternative to loops. So, in Haskell, which is a functional programming language, you actually don't have the ability to do loops like directly or normally the way that you would do it inside of a imperative paradigm. Instead, what you get is recursion. So all behavior that's accomplished by loops in other programming languages, such as Python, is actually accomplished by recursion inside of Haskell. So, let's examine our well-known factorial example. So factorial, defined once again as 1 if n is 0, and n times n minus 1 factorial if n is greater than 0. So you'll notice this term here is a re-invocation of the original definition of factorial inside of the definition of factorial. Now, this is what mathematicians would refer to as an inductive structure. So, inductive induction. Basically, it's a way of mathematicians having a fancy way of being able to get away with circular arguments. So, the idea here is that each time this definition is exercised, the value of n here is going to be reduced by 1. No matter how large n is, that means it will eventually reach 0. When it reaches 0, we hit a case where we no longer require the definition of the thing to define the thing. So we hit what's known as the base case. We can then use that base case to sort of back calculate the rest of these values. Pardon me. until we find the original value that we were looking for. So let's call up Python tutor and perform this calculation. Define factorial recursive n. If n is equal to 0, return 1. Else, return n times factorial n minus 1. And then calculate factorial of 10, for example. Well, you know what? Let's do like something smaller at first. 5. Good. So, we open up a stack frame with n is equal to 5, right? 5 is not equal to 0, so we enter this case, right? Which requires opening up another stack frame with n equals 4, right? Which requires n equals 3, which it requires n equals 2, which requires n equals 1, which requires n equals 0. With n equals 0, we have a return value of 1. Using that return value, now that we've hit an actual concrete value, we pass that up, right? Calculate the return value, pass that up, pass it up, pass it up, pass it up, and then we have the value, which is, in fact, we're not printing it or anything here, but the return value is 120. So, so that's how factorial works. Now you'll notice, I hope, that there is a reasonably direct, there's a direct correspondence between the manner in which this case, this mathematical equation has been written and the code itself. Like, this code is really just a complete and direct implementation of this mathematical formula. Ooh, I have a question. The first question today. Excellent. So eventually for recursions, we will hit the base case always. Now there's an interesting question. If you have designed your algorithm correctly, it will always hit a base case. If you have not hit it, if you've written the algorithm in such a manner that it does not hit a base case, then you will have a situation very similar to an infinite loop, which we call infinite recursion. Basically, since the execution of each function requires another function, if you never hit a case where you don't need another function, then you'll always need a new one, which means you'll just do that forever. So it's possible to get into infinite recursion in the same way that it's possible to get into an infinite loop. But it's maybe a little bit easier to remember to include a base case in recursion. Hopefully that answers your question. Thank you for the question. So, and this is, exactly what we did in Python Tutor. So, it may be instructive to add some print statements here so that we can sort of analyze what the code is actually doing here. So let's say executing factorial for n is equal to, and then the value of n, print base case in order to, I'm just going to split that up a little bit to be able to print a little easier. So, notice in our, this is our output pane. So, executing factorial for n is equal to 5. So, to calculate that, we need to execute factorial for n equals 4, 3, 2, 1, and 0, of course. Hit the base case, return 1. Then, returning 1, returning 2, returning 6, 24, 20. And then that's your return value. Right? So it's the thing I'm trying to illustrate here. It's not like the stack. It's not like the version of factorial that we open up to calculate the factorial of 5. That does not terminate until all the rest have terminated. So it's like the first one that's created is the last one to be closed, right? So it's kind of like, it's like different, it's like, I'm trying to think of a metaphor. It's like stepping into it, you know? We step into the next one, step into the next one, but we always have to return and close off all of the function calls that we've created so far. So there you go. Every time we recurse, the interpreter creates a new scope for the variables in the function. So this is applications of scoping to recursion. So if we slide in around here, you know, you'll notice that, like, we've got all of these instances of factorial open on the stack. We have, like, if we, you know, just for the sake of interest, created a dummy variable, right? Every single one of these stack frames has an instance of dummy, right? So each one of these has dummy at like its own local level. So we create that many copies of it. No matter which one of these you're in, the instance of dummy that you'll be referring to is the one at the most local level, right? So if you were inside of, like, the n equals 1 stack frame, then that's the dummy, that's the version of the dummy variable that you would be using for this particular instance, right? So there's a taste of recursion. Why would I be showing you this? So given that anything you can do with recursion, it is possible to do with a loop, right? And vice versa. Why would we care about such a convoluted technique? And the answer is, there are certain classes of problems which express themselves much more easily and readily as a recursive algorithm than as an iterative algorithm. So, if you have a problem that has an inductive structure, recursive algorithms are fantastic. You can, like, often drastically reduce the number of lines of code that you need. And your algorithm can be more efficient if it's recursive. For some types of problems, however, recursion can be an inefficient solution. And we're going to examine we'll examine another algorithm which has a inefficient recursive solution, assuming you don't do certain things to it first. So let's consider the Fibonacci sequence. Let me hear a whoop whoop in the chat if you've heard of the Fibonacci sequence before. / have you ever seen like a Dan Brown, a novel, movie, Dan Brown movie / read the novel? At any rate, the Fibonacci sequence is a very famous numerical sequence that actually has applications in terms of spirals, which is interesting. Awesome. So the Fibonacci sequence, roughly defined, is every number in the sequence is the sum of the two previous numbers in the sequence. And the first two elements of it are 1 and 1. Or, actually, one of my TAs pointed out to me that it's actually totally incorrect if the first two elements of the sequence are 0 and 1, because 0, 1, 1, 2, 3, 5, 8, etc. So that's the Fibonacci sequence. So let's write a recursive algorithm which calculates it, shall we? Let's do this also in Python Tutor. Tutor. So. Nope, I don't want to do it in Python Tutor. I want to do it in this. Topic 5. I'll make a new file. There we go. So, def fib n if n is equal to 1 or n is equal to 0, return 1. Otherwise, return fib n plus, or n minus 1 plus fib n minus 2. And let's calculate fib of 10. And just for fun, I'm going to time this. So time Python 3 topic 5 dot py. Oh, we should actually return the result, shouldn't we? Heh. There we go. So, the 10th Fibonacci number is 89. It takes us 0.023 seconds to calculate that, which, you know, is pretty fast. How about 20? Takes us, so there's the number. Takes us 0.031 seconds, so takes a little bit longer to calculate that. What about 30? Ooh, starting to get a noticeable delay. 0.2 seconds to calculate that. What about 31? 0.272. 32. 0.445. 33. 0.700. And if we just sort of skip up to 40, you can see it actually takes quite some time. So, this is a very simple algorithm. It doesn't really, intuitively, it doesn't make a lot of sense why it should take 20 seconds to calculate the 40th Fibonacci number, right? So, let's modify the program slightly to see how many times this recursive function is being executed. Because that's going to tell us why it's taking so long, right? So, let's say times run is a global variable. Global times run is times run plus equals 1. Print fib number equals this. Print number of calls to fib equals times run. And let's start that back at 10 again. So, back at 10, it requires 177 calls to the Fibonacci function to calculate the 10th Fibonacci number. For the 20th, it takes 21,891 calls. Increasing that by only 1, you'll see we almost double the number of function calls required. And that's the thing. So that is the entire pattern. Every time we increase the number we're trying to calculate by 1, we are almost doubling the number of calls to fib that's required in order to calculate it. So by the time we hit something large, in this case, like 38, you'll see that we're calling this poor function 126 million times. And it takes about 12 seconds to do so. Because, 100 million is a fair number of times to do anything. So the question is, why? Why do we have this huge number of calls to fib? And the answer is contained right in this line right here. What techniques can we use to make it faster? Oh ho, my friend, we're getting there. Do not worry. Do not worry. So, before we can intelligently make this faster, we have to know what the problem is, right? So the problem here, there are two problems going on. Number one, because this line contains 2 calls to Fibonacci, not just 1, each time Fibonacci gets called, and it's not 1 or 0, we're actually spawning 2 additional calls to Fibonacci. That's why the number of calls almost doubles each time. So, we might also make some observations about this. We might note that if we were to actually look at what it's being called, if we were to calculate fib 4, right, we would have 1, 2, 3, 4, 5, 6, 7, 8. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9. Would have 9 calls. And I'm sure if we actually run that, we'll get the same amount, but let's just do it to empirically verify. Yeah, number of calls to fib, 9. Right, so this is the structure. You may notice that there are some repetitions inside of this structure, right? You'll notice that fib2 is called twice. Each time it's called, it has to completely recalculate itself. So you can imagine, if you were trying to calculate fib5 requires fib4 and fib3. Fib4 would have to be calculated twice in that case, right? Fib4 would be calculated once, but fib3 would be calculated twice, once for calculating fib5 and once for calculating fib4. So this entire branch would be repeated. What it's not doing is it's not remembering values from different calls, right? So we're going to use a technique called caching, which is a storing of intermediate results to allow us to spend a little bit of memory and gain a whole lot of runtime. Question: can I explain the inputs/outputs for a recursive function? Yeah, so, well, the inputs and the outputs are defined just sort of exactly the way that they would be in any other case. In the case of the factorial function, the input is n, it's the number you're trying to take the factorial of, and the output is, that factorial number. What gets a little bit tricky is the way that the inputs are modified as we go through all of the different recursive calls. Remember that the return value is going to be substituted into the expression in the calling function when it's finished, but not until it's finished. So essentially, by the time you hit like the 10th level of recursive call, you've got basically 10 of these expressions that are all waiting for a return value so that they can calculate their final value, right? But yeah, I think you'd have to be a little bit more specific what you're talking about there with that question. So let's spend a little bit of memory to gain a whole lot of runtime. Let's create a memo. This is a technique which is known as either caching or memoization. Memoization because we're keeping a memo. So let's keep a memo that is an empty dictionary, right? Let's modify this so that we don't have to recalculate fib each time. We check to see if the Fibonacci number that we're looking for is already in the dictionary. If it is in the dictionary, then we just pull it from the dictionary, which is a much simpler operation than recalculating it. And if it's not, then we add it to the dictionary. So, if, and for this dictionary, we're going to assume that we're using the Fibonacci number that we're going to use the input to the Fibonacci function as the key to the dictionary. And the value of the dictionary will be the calculated Fibonacci number. So, if n-1 is in the memo, we do something. If n-2 is in the memo, we do something. else we do something else. So we said if it's in the memo, we want to use it from the memo, right? So we say, shall we say, x is equal to memo at n minus 1. Y is equal to memo at n minus 2. Return x plus y. Otherwise, we add it to the memo. So memo at n minus 1 is equal to fib at n minus 1, or fib with n minus 1 provided as an argument. And then we pull this line in again. And then we repeat that, for this case, modifying values appropriately. Now, I just want to, there are some simplifications we can make here, but I'd like to just demonstrate that this works before we get there. So, let's print, in this case, memo, the state of the memo each time that fib is called. Oh, and one other thing, because it's a default parameter, we should provide the updated memo to the recursive calls of Fibonacci. There we go. So, let's try it now. So, you'll notice that for fib 4, the number of calls to fib is now gone down from 9 to 5. If we want to calculate something larger, like 20, this is not working. I'm going to have to put it here, I think, to actually view. Yeah, there we go. Let's tone this down so we can actually see what's going on with the memo. So the way that this works, right? We're essentially getting to this guy each time until he hits a base case, right? Then the memo is built up from the bottom to the top, and you can see that this is basically just a listing of all of the Fibonacci numbers up to, the 9th, at which point the 10th is calculated as the sum of the 8th and the 9th. But most interestingly, we have reduced the number of recursive calls. Remember that in the case of 10, the number of recursive calls was 177. It's now only 11, which is a vast improvement. So yeah, that's how you make this better. Now let's talk a little bit about ways that we might make this algorithm slightly more efficient. So first of all, anytime you have a statement on both the true and the false branch of an if statement, it doesn't even need to be in the if statement at all. You can actually just pop it outside, right? So if we have if condition nothing else something else, we should eliminate the else case and say, and negate the condition. So if n minus 1 is not in the memo, do this, right? And we can apply the same transformations here to the y case. Clean the code up just a little bit, make it a little bit nicer, more presentable. Maybe even group these statements. And there you go. How's that for nice and clean and compact? Boom. So you can see by, like, just adding... So, yeah. So by just using a little bit of memory to store some intermediate results, we get a huge, huge increase in our efficiency for this algorithm. So there you go. Let me just... Okay. So one momentary digression on the subject of infinite recursion. It would be very easy to mess this up in such a manner that we would get infinite recursion. If we forgot one of these base cases, essentially what would go on is one of these, like, if we had, let's say you had 1, 1, 2, 3, 5, right? If you were trying to calculate the Fibonacci number 2, if you only had the base case on 1, right, 0 would enter this else case, which means that it would go back into, like, negative numbers to see if it could continue to calculate the Fibonacci number, which means that would result in infinite recursion. The way that looks in Python is you get a recursion error, maximum recursion depth exceeded in comparison. You can, I believe I recall, you can hit 1,000 recursive, like, a recursive depth of 1,000 before it will start complaining at you. And I think you can lift this restriction as well. But yeah. So that's how you can cause infinite recursion, and it's like infinite recursion will cause you either one of two problems. You'll either end up with an error like the one that we just saw, or you will have, like, it's not quite as bad as an infinite loop, right? With an infinite loop, the computer will literally never, like, recognize that it's in an infinite loop. With infinite recursion, you will eventually, sooner or later, you're going to use up all of the memory that's available for the system call stack, and you'll cause a stack overflow error, which is an operating system error, right? But it's not going to just hang forever, infinite recursion. It will eventually result in either a programming language error or an operating system error. So in that sense, it's, like, slightly better than infinite loops, but, you know, not great still. Pardon me. So, this kind of brings us into a discussion of the efficiency of programming languages and the efficiency of algorithms. Well, not languages, algorithms. So, in general, we have two ways of estimating the efficiency of an algorithm. The general problem with measuring the efficiency of algorithms is that algorithms are almost always run on, like, widely different hardware, right? So, you know, just because this algorithm took, you know, 0.714 seconds to execute on my computer, that says almost nothing about how much time it's going to take to execute on any of your computers. In fact, if I were to run the same algorithm several times, you'll see I get several different run times each time, right? Like, basically every time I run this, I'm going to get a different runtime, and it has to do with a lot of things like like how much of the system's resources are consumed by other processes, and, all kinds of there are too many factors to name, right? So, what we try to do is we try to derive not just practical measurements of how efficient an algorithm is, but we try to analyze things from a theoretical perspective as well. And in theory should line up with practice. So, from a theoretical standpoint, runtime complexity can be measured based on the structure of the program itself, right? How many loops do you use? How nested are those loops? How many statements are you executing per loop? All of these things, are these recursive? To what degree are they recursive? How many are you spawning one new instance of this function, or two new instances of this function, or 5 new instances of this function for every recursive call? These factors can be used to arrive at a theoretical understanding of how much time an algorithm will take to execute. You can perform a similar analysis on memory, right? How many variables are used? How many frames on the call stack will be required? How many variables do each of those calls? How many variables are used by each of those calls? Do you require any memory? Do you require, do you require the square of the number of input bytes as the amount of memory that you're going to require? All of this kind of stuff, right? Memory complexity also is a factor. In practical terms, both of these things can be measured. In Linux more easily than in other places. So, in Linux we have this nice little time program which just times. It's like a stopwatch utility for programs, right? We can measure how many seconds this runs for a particular input, right? In theory, a large number of inputs, you could run a range of inputs of increasing complexity, derive a mathematical formula from the runtimes versus the inputs. Memory is similar. We can measure how much memory a program uses. So, if we were to time runtimes of fib versus, the number we're trying to calculate versus the runtime, according to our old, the less efficient implementation. I'd just like to point out that my computer is better than the computer here that was used to run these tests by a factor of 50. I just want to point that out. Or wait, factor of 50? Factor of 5, I think. Never mind. Well, it's still pretty good. What was the runtime for 40? I think it was 20 seconds. 20 seconds, yeah, so factor of 5. Ha! My computer's better by a factor of 5. Anyway, so, we can plot this, and you'll notice, if you were to interpolate a function here, for the, we get basically the same information that we observed, which is, the runtime is exponentially related to the size of the input. The larger n gets, the more you're going to see the inefficiency, even though for small values, like say 10 and less, you're not even going to know that this is an inefficient algorithm. So we already showed memoization. with memoization, here are some practical runtimes as well. You'll notice, while we have a certain amount of operating system variance, roughly speaking, the amount of runtime varies linearly with the Fibonacci number that we're trying to calculate. So, you know, you can do better than this on certain algorithms, but for, you know, if your option is this function, which grows linearly with the input, and this function, which grows exponentially with the input, obviously this is a much better algorithm, right? Good. And now we're going to examine an algorithm which performs even better than linear time, which is kind of exciting. So, so we've talked a bit about search algorithms, right? We talked about linear search. The linear search algorithm is that you have to check every single individual element of the data structure to see whether or not it's the thing you're looking for, because you're not making any assumptions about the structure of the thing you're searching. If you can make some assumptions about the thing that you're searching, you can get a much, much more efficient algorithm. The property that we are going to apply to the data structure that we're searching is the property of sortedness. That is to say, we're going to assume that whatever list we're searching, we're going to assume that it's in order, right? So, so this, yeah. So, we're going to use an algorithm called binary search. The binary search algorithm is reasonably similar to the, you guys remember that that example we did, like the first example we did, where it's trying to find the x-intersect, and it's a bisection method. So we're narrowing down the range inside which the answer can be each time. Well, we're going to do a similar thing with binary search. So let's imagine, just out of interest, we had a series, like we had some data which was in order, right? And let's say we're looking for a number like 33 in this particular set of data, right? If we examine the middle element, right, because of the sortedness property of this array, nothing to the left of this number can be greater than it, because it's sorted, right? Everything on this side has to be less than the number in the middle. Since this number in the middle is itself less than the number we're looking for, we know that the number we're looking for must exist in the top half of this array. So, we can exclude from consideration half of the entire array, right? We can then perform the same operation recursively on this new subarray. We take a look at the middle element, in this case 43. We say, okay, so that's greater than the thing we're looking for. So the thing we're looking for cannot be this element or higher. So we can exclude those from consideration. And so we are left with the, this 3-element array. This is lower than the thing we're looking for, so if it exists, it has to be higher. And then we are left with an array that has just one element, which is not the element we're looking for, so we say, okay, we didn't find it. If we were to state this algorithm somewhat more formally, we look at each step, we look at the entry in the middle. If the middle entry is equal to the target entry, we found it. If the middle entry is bigger than the target entry, we only need to look in the first half of the list. If the middle entry is smaller than the target entry, we only need to look in the second half of the list. This is like the famous phone book example. Oh, I'm not familiar with the famous phone book example. Is it like you look up a name, and if it's like, you know, I don't know. I can imagine using binary search to look up names in a phone book more efficiently, but yeah, most people don't search efficiently. I'm just going to point that out. So let's do up an implementation of this, shall we? Let's do this one in Python Tutor. Def bin search takes some list and a number we're looking for. You're looking for a phone number, and you tear the book in half, and so the same thing like the binary search. Yes, yeah, you'd be able, because, so it's like the strength of this, and I'm getting a little bit ahead of myself, but the overwhelming strength of this technique is the fact that you're reducing the size of the number of numbers you have to care about by half each step. So, basically, this makes it a logarithmic algorithm, right? So, you can double the number of numbers that you're dealing with and only have to accommodate one more step, right? Or only have to run one more step. So, like, very, very quickly, like, you can process, like, 1 million inputs in, like, 10 steps with this, which is amazing. It's amazing runtime. Anyway, but let's implement it first, so. Pardon me. So, first we calculate the middle number, or the middle index. Middle is equal to the length of L integer divide by 2. If L at middle, I'm going to call it mid, is equal to n, return true. If L at mid is greater than 2, we do something. And if L at mid is less than 2, we do something else. In this case, if the mid, oh, not greater than 2, I'm sorry, greater than n, there we go. So if it's greater than n, then we know that the number we're looking for has to be in the first half of the array, right? So, return bin search of L from the beginning to the midpoint, well, 1 minus the midpoint, in fact, looking for the same value, n. Return, and in the other case, we're looking for the top half, so bin search L from midpoint plus 1 to the end. Notice I'm using list slicing for this. So this is all well and good, but we're missing a base case. If L contains no elements, then it's not possible that n is in it, so we'll just return false. Okay. And I suppose we could make these elifs if we really wanted to. Get out of here. Good. So, there we go. Sorted array, sorted list, sorry. Put that in there. Searching for element 4, just for the sake of interest. So we have our array. N is 4, right? We're looking for 4. We decide that the midpoint shall be... Did I get an error? Oh. Oh, yeah, that would be an error. Good lord. I'll blame it on the cold. I blame that on the cold. There we go. All right. Yeah. So, the midpoint is 9, so we know that the value at index 9 is 5. 5 is greater than n, so we enter this statement here, call bin search recursively on a subsection. This subsection, to be precise, all of the values here. So, the midpoint, then, is 4. The value of the midpoint is 3. So, we enter this case for the midpoint being less than n, which, of course, spawns a new instance of the binary search using the top half, right? We iterate this process again, grab the bottom half. The midpoint, in this case, will be 1, just because it's, when it gets down to this level, you're not really, the fact that there's no actual middle is kind of like, it'll still work. There we go. Now the midpoint will be 0, which is, of course, the thing we're looking for, so we return true up through the call stack, and boom! Everything is cool. So let's see what it looks like when we're searching for something that doesn't exist, like 8. So we keep moving, take the top half, take the bottom half, take the top half, and this is interesting, right? So we then start a new instance of binary search where L's pointing to an empty list, right? That empty list will activate the first condition, which makes our return value false. That gets passed through the algorithm as the solution and output, and there you go. So that's how it works if you don't find a thing you're looking for. Cool, right? So yeah. Here's the algorithm as given by the slides, which I think is reasonably similar to the one we did. So, Binary search using recursion is much faster because it only has to look at a small number of items in the list. If the list has length n, then the binary search using recursion looks at approximately log base 2 n elements of the list. So one thing to note about this, the way that I've been doing it and the way that you do it using recursion, it's not quite as efficient as it seems because, like, you have to keep in mind the amount of time it takes to copy out the new copies of the list, of the array, or the list, sorry. You can do all of this just keeping track of positions inside of the array. And then you don't have to, like, you don't actually have to copy the whole data structure, right? So, like, if you were to do a different version of this, say you had, you know, bin search 2. Let's do a non-recursive version. So A is equal to 0. B is equal to length L minus 1, because we want the index of the last element. Then while A is less than B, if midpoint, or if L at the midpoint is greater than, or is equal to, and we'll just, you know, keep that structure similar. Return true. Else, if L at the midpoint is greater than n, then we want the first half, right? So because we want the first half, we move the upper bound down, right? Oh, and we need to recalculate the midpoint based on A and B. Now that yeah, let's do this way. Recalculate the midpoint, so it's A plus B divided by 2. That'll give us the average. Or A by, wait, yeah. Yes, that'll give us the average position. Then, so if the number we're looking for, if the midpoint is greater than the number we're looking for, then it exists in the bottom half, which means we move the upper bound down. So B will then be equal to mid. Otherwise, we move A up. We do that until A is not no longer less than B. So if A and B are no longer less than or equal to each other, then if L at A is equal to n, return true, else return false. So you can see this looks a lot more like the Newton's method bisection method that we covered previously in class. Oh, I'm gonna have to actually execute it. I'll have to. There we go. There we go. So bin search 2. We set A and B. A is 0, B is 17. The midpoint is 8. So we move A up, right? The new midpoint is 12. We move A up again. So now we've got the range here, right? Midpoint's 14. We move B down, so it's somewhere in here. Midpoint's 13. We move A up, etc., etc. Uh-oh. Uh-oh. I think I hit an infinite loop. Gross. All right. Well, this will be informative for you when I fix this. So, the reason that we're hitting an infinite loop here is because each time we recalculate the midpoint, it's not changing. It's maintaining its position at 13, right? 13. B is 14. This is 13, right? So, we're constantly moving A up, even though it's not actually being reassigned to the same value. So, one way that you could fix this is you could say, add to the loop condition. Well, let me think. How do I want to do this? It's a bit kludgy, but if midpoint is already equal to A, then we do something else. Otherwise, we set A equal to mid. I think if we just break out of the loop, then I think that works. So here we're in the situation that's nasty. So midpoint and A and midpoint are both the same. So rather than get stuck in that loop, we break from the loop, evaluate it, return false, bing, bang, boom. So there you go. Good. So yeah, and that's what I just did here. Although this also uses a recursion as well. So it's possible to define a function inside of another function. These are generally called helper functions. But it's interesting because this function is now also scoped to this function. So it does not exist outside of the scope of the upper level function. Which you can find applications for. So yeah, I think we'll call it here so you guys have some time to get some lunch before your tutorials start. So I apologize for having to move things online relatively quickly. I hope you enjoyed the lecture insofar as I was able to deliver it under current circumstances. But yeah, thank you very much for your indulgence. I'm sure I was not easy to listen to today, but yeah. Tomorrow we'll have a live stream as well, eh? How do you sort a list or a tuple? Now there's a question. So sorting a tuple or a list, you know, let's say we have like an unsorted list, right? If it's a list, you can just call L.sort and that sorts it. But, you know, the question, of course, is what is sort doing You know, how does the sort actually work? Sorting algorithms are a whole subject of study. You know, there are actually a large number of sorting algorithms. You know, you've got bubble sort, merge sort, quick sort, shell sort, insertion sort, lots and lots of different sorting algorithms. So it's kind of a topic for another time. But if, in terms of practicalities, if you want to sort a list, then this is how you do it. Tuples. This is, of course, a method which does not apply for tuples. So if you have a tuple, right, and you want to sort a tuple, something like that, you can't just say t.sort, because tuple object has no attribute sort. So what you do is you say, give me a list, sort that, and then tupleize it. Ah. Interesting. Oh, assign it to an intermediate variable. There we go. L2.sort. And then tupleize it. So, there you go. One important thing to note about sorting and the binary search algorithm. Sorting actually takes more time. Like, it's not a linear algorithm. Like, even the best sorting algorithms can't sort in linear time, and they certainly can't sort in logarithmic time. So if you're applying a sorting algorithm in order to be able to apply the binary search algorithm, you're going to be losing time versus a linear search. So, also, will the material we study on the 24th come on the midterm? Oh, good. Let's see, is everybody logged off yet? No, okay, people are still paying attention. So, I'll talk about the midterm in more depth tomorrow, but, like, roughly speaking, in terms of coverage, let me just pull up the syllabus here. I certainly won't test you on stuff that's covered the day of the test. That just seems cruel. And, you know, I might have a certain reputation for a degree of cruelty, but there are limits even to the amount of cruelty that I am willing to countenance in this course. No, your testable topics are these ones. Right? So, basically, material from the first 2 assignments is testable, and that's it. So, there you go. Any other questions? Ah, that's kind of funny. We're studying testing on the day of the test. That's funny. Huh. So we will be good for the midterm by the end of tomorrow's lecture. Yes. All of the material that will be covered on the midterm will be covered as of this time tomorrow. So there you go. Good. Alright. Take her easy, folks. I'm going to sign off here. Keep it real. Stay frosty. And don't do anything I wouldn't do.